For the remainder of our fundamental identities problems, let's go ahead and take a look at example 2. We are asked to factor the expression. We have sine squared of x minus cosine squared of x. Here our goal is not to simplify, but to factor. So what I'm seeing here is difference of two squares. This is a very commonly used formula in this sort of problem. If you have a squared minus b squared, that is equal to a minus b times a plus b. So we're going to use this form to factor the first expression. Sine squared of x minus cosine squared of x is equal to sine of x minus cosine of x times the sine of x plus the cosine of x. And that is our final answer. For part B, I'm going to switch colors so you guys can read that a little bit easier. For part B, we have 6 times cotangent squared of x minus 13 cotangent of x plus 5. Doesn't that kind of look like a quadratic equation? What if I asked you to factor 6y squared minus 13y plus 5? See if you can factor this expression out. To factor it, it might be helpful to find the product of 6 and 5. 6 and 5 is equal to 30. 6 times 5 is equal to 30. And now we're looking for two numbers that multiply to give you 30 and add together to give you negative 13. That would be negative 10 and negative 3. We're going to use these negative 10 and negative 3 to break down the negative 13 and then use grouping. Let's switch back to the cotangent example and see how that works. I'm going to rewrite my expression as 6 cotangent squared of x. And instead of negative 13 cotangent of x, I'm going to say minus 3 cotangent of x minus 10 cotangent of x plus 5. How do I know that these two numbers are going to work? That's why I multiplied 6 and 5 together, got 30, and then I used the quadratic factoring rule of product, that the product is equal to 30 and then their sum is equal to negative 13. So out of the first two, 6 cotangent squared of x minus 3 cotangent of x, we can factor 3 cotangent of x. In the parentheses, we're left with 2 times cotangent of x minus 1. From the next pair, we can factor out minus 5. If we factor negative 5, then we're left with 2 cotangent of x minus 1. Oh, look at that. We have a common factor again. So then we can factor 2 cotangent of x minus 1, and in the next set of parentheses, we're left with 3 cotangent of x minus 5. And this right here is our factor form. In the next example, we have to do something similar. Once again, we have to factor. The problem here is I can't factor x squared minus 2y minus 7. I need to have the same expressions over here. So whenever you see so many different expressions, what you want to do is try to change those into the same thing. So let's take a look at a Pythagorean identity. Maybe we can use something there. One of your Pythagorean identities uses cotangent squared of x. So we can replace cotangent squared of x with the cosecant squared of x minus 1. This was found from the Pythagorean identity that uses cotangent squared of x by rearranging the terms. And then I have to copy over the remainder of my expression, which is minus 2 cosecant of x minus 7. Now I would take a look and see if there's anything I can simplify. Well, I have cosecant squared of x minus 2 cosecant of x minus 8. Now it looks just like a quadratic equation of the form y squared minus 2y minus 8. And to factor it, I'm looking at two numbers that multiply to give me negative 8 and add together to give me negative 2. Those numbers are negative 4 and positive 2. Okay, so we're ready to factor our expression. Here I have cosecant of x plus 2 multiplied by the cosecant of x minus 4. This is where you pause and you ask yourself, does that make sense? Well, you can use FOIL or distribute each one of your terms and see if you do come back to your previous line. But this would be your final answer. Let's take a look at the next example, example 4. We have cosecant of t times secant of t minus sine of t times secant of t. Well, the very first thing that is easy to see is that you can probably factor something out. So we can start by factoring this secant of t. However, the way that I have that figured out is actually through conversion to terms of sine and cosine. If you have a different strategy, I would love for you to share it with the class. Let's take a look at what happens if you convert everything in terms of sine and cosine. We get 1 over sine of t times 1 over the cosine of t minus the sine of t times 1 over the cosine of t. Okay. Now everything is in terms of sine and cosine. We only have two numbers to worry about. It looks like we have a fraction minus another fraction. If I want to combine those two together, I need to find the common denominator. The common denominator is sine of t times cosine of t. So it looks like what I am missing right now is sine of t. So I'm adding this in green just so I can find a common denominator for these two fractions. Once I have that common denominator, I can go ahead and combine these expressions together. We have 1 minus, from the right fraction, we have sine of t times sine of t. So we have 1 minus sine squared of t. And then we have a common denominator of sine of t times cosine of t. Over the top, I'm seeing ones and squares. There must be a Pythagorean identity that I can use. 1 minus sine squared of t is equal to the cosine squared of t over the sine of t times the cosine of t. We can simplify one of these cosines. We're left with cosine of t over the sine of t, which is really the cotangent of t. And that is the final answer. Once again, there might be a different strategy that you can use. This was the first one that I thought about. If you did come up with a different solution, please make sure you share that with us tomorrow in class. And lastly, let's take a look at example 5. Okay, in example 5, we're asked to rewrite this expression so that it is not in fractional form. That means that somehow I am going to try to eliminate this 1 plus cosine of y. So a tip that we can use here is that you can rationalize. Or another tip is that you can use the difference of squares. But wait a minute, I don't see any difference of squares right now. What I do see is 1 square. We have sine squared of y. I want you to look at the Pythagorean identity and see what you can replace sine squared of y with. It looks like sine squared of y is equal to 1 minus cosine squared of y. So we're going to do that first. I start by writing out my original expression. Then we're going to replace the sine squared of y with 1 minus cosine squared of y. And I still have the same denominator, 1 plus cosine of y. Oh, now I do see a difference of squares. I really have 1 squared minus cosine squared of y. That means that the numerator is really equal to 1 minus cosine of y times 1 plus the cosine of y over still the same denominator of 1 plus cosine of y. It looks like I have 1 plus cosine of y, some number, divided by the same number. That means that I can cancel those out, and the answer is 1 minus cosine of y. If you are also opening the solution of my worksheet, I actually worked it out in a different form in that solution. So please take a look at that solution. It is slightly different, however, the answer is still the same. In the solution worksheet, I worked it out by rationalizing the denominator, and it's still canceled out to a final answer of 1 minus cosine of y. Thank you guys, and I'll see you tomorrow.